Okay, folks, it is time for a new video. This one is on how to deal with certain types of savings accounts that you really never have dealt with before. And this one is what we call the monthly savings plan account. Um, so in pre-calc, you've probably did a little bit of work with simple and compound interest, and like money goes into an account for X number of years. How much money do you have at the end, right? You've done those, you've solved for all those different variables. We did that in previous videos. Um, but to be perfectly honest, that's not the way most accounts work. Yeah, there are people that are able to put just one chunk of money in and let it sit. But generally speaking, if you have some sort of employer-sponsored plan, or you are, trying your best to save money as you go through life, you're going to be putting money into an account at regular intervals rather than at one given time. Like usually most people don't have $30,000 put into an account and let it sit for 20 years. Awesome if you do, but most people might put just a bit in at a time. Um, so we're going to cover situations like that. So here's kind of the way that we're going to kind of introduce this. Suppose every workday you go to Starbucks and you buy this is funny, a $6 venti half whole milk, 1/4, 1%, 1/4 non-fat extra hot split quad shots with 1.5 decaf, 2.5 regular, no foam latte with whip, 2 packs of Splenda, 1 sugar in the raw, a touch of vanilla syrup, and 3 short sprinkles of cinnamon. Okay, yes, that is an actual Starbucks order. I asked a friend of mine who works at a Starbucks down in Florida what was the craziest order that he generally gets at his restaurant, and this is what he told me. Um, so, wow. Okay. Now, there is an issue here. First, you're an insufferable millennial, and I know I'm poking fun of myself. I am technically a millennial. Um, The other problem, though, here is that you need to save money for retirement. If you're buying stuff like this, probably you have enough money where you don't really need to care about retirement. But what if you do? Okay, so here we're spending all this money. We're spending $6 a day buying this, whatever this is, every workday for years and years. Okay, so this, as you can imagine, can add up to a lot of money. I mean, just simply put, $6 5 days a week is $30 a week. So that's what, $120 a month? $120 a month for how many months? That can add up. And then you put interest on top of that if you put this into an account. Wow. Okay. So, what we're going to do is figure out what if instead we did this. We take the money and instead of spending the money on this coffee, maybe we make our own coffee, maybe we go without coffee. We deposit it once per month into a market-based IRA. Every month, our entire career of 40 years. Over the long term, let's say we get 7% return. That's pretty common year after year. If you break it down in terms of stock market for years and years going back to 70s, 80s, whatever, it's about 7% per year. Give or take, obviously certain events change that, but 7% is a pretty good estimate. How much money are we going to have at the end of this? Well, okay, let's find out. So a couple things here. First off, as you can tell, there's going to be some differences here to the calculations that we've already done. Um, so we'll have to go over what formulas we need, the calculations, how to do them, and some different ways that we can use this formula. Okay, so the number one thing to realize here is that we're not putting the money in all at once. Each amount is going in at different times and will accrue different interest. All right, so once again, we have to go back and look at the situation as a whole, right? So we need to develop a formula for this. And since we're doing this in the form of a video, I'm going to take the time now and actually develop the formula for this in a way that I hope makes a little bit more sense. This is especially aimed at people might have more of an interest at how these formulas come about. You can feel free to skip this part if you don't need to know the derivation of the formula, but I'm going to put this in here simply because I didn't have enough time in class to really truly go over how this formula develops. Okay, so let's go for it. So let's look at what's happening in this account, all right? So once again, we're going to assume, for our purposes here, let me make sure I've got a page. All right, so we're going to go and actually set this up, right? So we are putting in, we have said $120 per month. So let's go ahead and write that down. So we're going to put in, oops, as I find a way to clear it. Okay, so we're going to put in $120 per month. Okay, so for 40 years. Now 40 years times 12 is 480 months. Okay, so here's the deal. The first $120, okay? The first $120, okay, it's going to go into the account and it's going to sit in the account for 480 months, okay? So if I were to do this formula just with the 120, let's say I put $120 in just once, right? And I put it in once and I let it sit for 480 months or 40 years. What would that formula look like? According to our compound formula, it'd be 120 parentheses 1 plus 0.07 divided by 12 for monthly to the exponent of 480 because it would be in there for 12 times 40 years, okay? So 480 months, and then that will come out to a value. Now, I could go ahead and calculate that value, but I'm not going to yet. But that's the way that you would calculate it. Okay, what about the second $120? Now, the second $120 is going to go in, and it's going to go in for the second month. But guess what? It's going in for the second month, right? So it's not in there for the first month. So how long is it in the account for? It's in the account for 479 months because it's not the first month. It's there from the second month on. So the formula for that, 120, same interest rate, same compounding, but it's in there for 39 years and 11 months. That's 479. And now we'll have an answer. What about the third $120? That's in there for 478 months, not present for the first two, but present for the third, and so on and so forth. So that one's going to be in there, 120, 1 plus 0.07 divided by 12 to the 478. Okay. You start to see a pattern here, right? It's going down one each time, all the way down to the final $120, okay? The final group of $120 is only in there for the final month, okay? So it's only going to be in there for final month, and so it's going to be 120, 1 plus 0.07 over 12 to the 1, okay? And so this pattern is going to continue all the way down to 1. Okay, now here's the thing. The presence of interest doesn't make other interest gain more interest. So all this is simply additive. So all we have to do is find all of these and add it together. Wow, well this is pretty tough. Because does that mean we have to do 480 different compoundings? Yikes. Okay, so how do we handle this? Well, there's a couple ways we can do this. But the best way is to let's write it all out. So let's change page. And so really what we're going to do is we're going to write this as a sum, right? So the next page, what we're going to do is this is equal to the total amount in the account is equal to 120 times 1 plus 0.07 over 12 to the 480 plus 1 plus 0.07 over 12 to the 479 plus 1 plus 0.07 over 12 to the 1 power. Okay, now the reason why I'm able to do this is I was able to factor the 120 out of each and every term because all of them have this factor of 120. So I just factored that out, which just leaves me as the sum of all of these powers, okay? Now, what I can do, I'm going to switch colors here, okay? And go. So now, let U equal 1 plus 0.07 over 12, okay? So now what I have, I'm going to let U equal this, just so that I can write this in terms of a variable. So now what I have is I'm going to write this in a little bit of a better form. Equals 120 times U to the 480 plus U to the 479 plus U to the 478 plus plus U squared plus U to the first. Okay. So the question now is, what the heck do I do with this? How does that allow me to add it together? Well, it turns out that there is a pattern to this, and this polynomial here that stretches from U to the 480 all the way down to U to the 1, it turns out that this, believe it or not, is factorable. And it sounds crazy that it would be factorable, but it is. So the idea here is what you wind up having to do, I shouldn't say that. It's not factorable as is. So what we'd have to do is we have to look at this problem a little bit differently. So I'm going to open up a new page here, okay, and just kind of show you what's going on. So with this particular problem, this has to do with a situation like this. So you might remember from pre-calc or even from algebra 2, there are certain expressions that factor, right? Okay, and here's one that's common. If you had U squared minus 1, this is equal to U plus 1 times U minus 1, okay? But there's some other ones. Now, if you're really good, you might remember ones like this, U to the third minus 1. This is called the difference of cubes. And it turns out that this one, if you remember your difference of cubes pattern, that's okay if you don't, you can take my word for it. This is equal to U minus 1 times U squared minus U plus 1. Sorry, plus here. So, and this there's this very particular pattern for this. What about U to the fourth minus 1? Okay, so U to the fourth minus 1, this is equal to, well, let's write it as a difference of squares first. As a difference of squares, it's U squared plus 1 times U squared minus 1. Okay. Now we know this multiplies out, so it becomes U squared plus 1, U plus 1, U minus 1. Okay, well, guess what? Now I'm going to do a clever trick here. I'm going to multiply these two together, and I'm going to create, I'm going to come up with U to the third, okay, plus U squared plus U plus 1 times U minus 1. So here's a crazy situation. Take a look at this. every time I have u squared minus 1, u to the third minus 1, u to the fourth minus 1, it's equal to u minus 1 times some collection of powers. And so here's what this now means, okay? So we can generalize this, okay? Okay, so we can generalize this. Now, again, this is, hopefully this makes sense if you've done pretty well in pre-calc and maybe you remember some of your factoring terms. But we can generalize this. If I have u to the n minus 1, this is equal to u to the n plus u to the n minus 1 plus u to the n minus 2 plus dot, 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 plus 1, all the way down to 1, multiplied by u minus 1. And so what does this have to do with the expression that we're doing with trying to create this savings account? Because now I have this sum here, this entire sum here. If I divide both sides by u minus 1, now I have u to the n plus u to the n minus 1 plus u to the n minus 2 plus dot 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 plus u plus 1 is equal to u to the n minus 1 over u minus 1. So it turns out that that entire sum is equal to u to the power of that highest exponent, minus 1, divided by u minus 1. Okay? And so now that we have this, guess what happens now? I'm going to bring this back. And I'm going to bring this back now to this expression here. Do you see how this now becomes this expression here? Okay. Okay. So yes, the only problem now is that it does eventually end on 0 or 1 instead of 0. But that's okay. We can put in a u to the 0 term as well, if we want to let it sit for one more term than that. So technically, now that I'm thinking about this, what we can do is we can realize that that first $120 that goes in, that first $120 actually doesn't get interest the first month. Because when we put it in, we're going to be putting it in directly after that first period of interest. So technically, this happens. This is actually only in for $479. And this is only in for $478. And then the last one goes in, but no interest actually ever gets applied to that one. So what winds up happening is you get a situation where you have this going from 480 all the way down to 0. So there's a little bit of a hole here in terms of whether this starts at 480 and goes all the way down to 1 or goes all the way down to 0. I understand that, but essentially here's going to be what happens. This now essentially becomes 120 times u to the 480 minus 1 over u minus 1. And u is equal to this expression here. So in the numerator, you're going to have this with the same exponent of 480 minus 1 over, in this case, u minus 1. By u, you're going to have this 1 plus, and it's going to cancel out with this minus 1 here. So this formula takes a little bit of finagling. But this is the end result. You can kind of see where this formula now develops. The formula looks like this. So this is called the systematic savings plan formula. And it relies on the fact that this expression here on the right side represents the sum of that entire power series from where it starts all the way down to 0. So this formula assumes, now that I'm realizing it, this formula assumes that you make not 480 deposits, but 481 deposits, with the last one included that has no interest in it. I'm realizing that now, but that generally doesn't change the formula too much. So here, D represents the deposit period per period, and that's monthly. So a couple of things here about this formula. As before, with all the previous formulas, R and T will always match units. So in this case, it'll always be years. So T will be years, R will be an annual interest rate. The other big thing here is that N will match amounts with D, which means is that if N is compounded monthly, then D, the deposit, will also be monthly. So the compounding for this formula will be the same as how we deposit. Again, it's usually monthly, but if it's quarterly, like if we have an N being quarterly, then the deposits that we get when we solve will also be quarterly, okay? And you'll see how that plays into account, okay? All right, so here's the formula. Now let's see if we can actually apply it to this problem, all right? A couple things here. One, deposits and compounding happen in equal intervals. So that's what we said before. If monthly, then monthly. If quarterly, then quarterly. Interest rate is fixed, deposits are uniform and regular. So no skipping deposits, nothing like that. That always happens. The deposits happen at the end of each period after the period interest. So what winds up happening is, assume after period interest, that's why the final deposit is after the period's interest, so the final deposit has no interest applied to it. That's why we end up with one more deposit than usual. Okay, all right, so let's take a look. We work, consider the original problem. We work 20 days per month, so $6 a day, 7% interest, 40 years. Okay, so let's fill it all in. So here, D is 120. Oops. So D is 120. Wow, that came up. Wow, what's happening here? Okay, so my marker is acting up a little bit. Let's see if we can't fix that. Okay, so we are looking at 120. Why is this acting up? Oh, this is strange. Okay, 0.07. N, we're going to be doing monthly deposits, so N will be 12. And then T will be for 40 years. Okay, so let's plug it all in. So, okay. Is that right? Okay, so my pen is just acting up a bit. All right, so let's see. So let's try it again. 120. Parentheses. So again, so our new formula, we're going to start the same way we usually do. It's going to be 1 plus 0.07 divided by 12, parentheses, 12 times 40, which is 480, minus 1 divided by, and this time it's just going to be R over N, 0.07 divided by 12. Okay? So that's the way this formula will work. And if you look here, you'll see exactly that. Let's go back. So 1 plus R over N to the NT minus 1 divided by R over N. Okay. All right, so let's see what happens when we do this, okay? So again, when we do this in the calculator, let me pull up my calculator here. Let's do that. So the calculator is going to come up. We're going to do this on the big TI-80 4 so that we can see how this reacts. Okay? All right, come on. Go up, calculate. Oh, there it is. We got it. All right, it came up. Okay, so when you do this in the calculator, okay, the best way to do this is I always start with the numerator first. So watch what I type in, parentheses, 1 plus 0.07 over 12 exponent. Now, if you've got a calculator that shows you the exponent, if you want to do 12 times 40, you can. You can do that prior and know that number, or you can put it in parentheses. I already know that number, but if I have here, I can do 12 times 40. Why don't I do that? Just for sake of completeness, minus 1. I'm going to get enter. Okay, 15.3111. Okay, so that's the numerator divided by parentheses 0.07 divided by 12. Okay, 2624.81, but we're not done yet because that's the total number of groups of the 120. We're going to multiply by 120. 314,977. That's the total amount of money that this generates. $314,977. That's some expensive coffee right there, folks. $314,977. Okay, so that's how we use this formula when we have to plug everything in. If we ever have to solve for f, which is the future value, that will sometimes happen because this is equal to f here, so f equals this. Sometimes we're given the future value, like how much do I have to put in a month to reach, say, 500,000, 500,000. If we had to do that, then all we have to do at the end is simply divide the future value by whatever the calculation here. So I can still calculate this, and then I just divide my future value by that. So we'll do an example of that in a bit, right? So we've done the calculation. Okay, here's a good example. Suppose we need to save $250,000 for college for a kindergartner. Okay, our kid is 5 years old, and we've realized, oh, we need to start a savings account. So we set up a fund that gains 8% compounded quarterly. All right, so let's write it all down. Okay, so F equals, we need $250,000. D, we're trying to find how, like, we must know what the quarterly deposits have to be. R must be 0.08. Now N is compounded quarterly, so we're going to do 4. And T, well, what's T in this case? So we've got a college fund, okay? So it's a college fund for a kindergartner. They're 5 years old. Well, when do you go to college, right? If they're in kindergarten, they've got to go through kindergarten and they've got to go through grade school, so that's 12 more years. So we're going to do this for 13 years. Let's set up the formula. 250,000 equals parentheses 1 plus, so we have this D here, we need to find D, 1 plus 0.08 over 4, parentheses 13 times 4 minus 1 over 0.08 over 4. Okay. Now in this particular case here, we can simplify this. 0.08 divided by 4 is 0.02. And we know that 13 times 4 is 52. So why don't we just go ahead and simplify this a bit. We can simplify it or we can put it into the calculator as is. Maybe again, even though we can simplify this, I'll just put it into the calculator as is. Again, this is good practice because you can't always simplify it, right? Parentheses. Start with the numerator. 1 plus 0.08 divided by 4. Parentheses. Exponent 13 times 4. Minus 1, I get an answer. Divided by parentheses, 0.08 divided by 4. Do not forget the parentheses. If you do, you are going to end up in a completely different location. 90.01. And we're going to now, instead of multiplying, since I need to find the deposit, I am going to divide this value into the 250,000. To do that, I do the following. 250,000 divided by, now I could type that number in, or I get it second and the minus sign, and that brings up ANS. 250,000 divided by previous answer. If you want to just type it in, you can do that too. 2777.27. Okay. That's huge. That's how much money per deposit. Now that's the deposit amount because we compounded quarterly. That's the amount quarterly. Now, when something happens quarterly, that's 4 times a year. So 4 times a year is 3 months. So if I divide this by 3, that's $925 a month. Now, putting in $925 a month will get you a slightly higher value than this because now you're getting interest. You're getting more interest at different times. So, which is, interesting to think about there. Actually, wait, no, if you compound it the same, but you put it in, you could just simply divide and it will just do, okay, no, maybe it won't matter. Okay, so it's going to be about $925 a month. That's a lot. But think about it. You're trying to get $250,000 in 13 years. So you have to be aggressive at saving for that. Okay. Here's another question. What happens if instead of a kindergartner, what if we did it from the moment they're born? Okay. So if we did this here, so this is $925 per month. Okay, but what if we change this from the moment they're born? We change that to 18. How would this change your answer? Let's go find out. So we're going to go back up to our calculations and we're going to change, all we have to change is this 3 becomes an 8. We get a new answer. We're going to divide by the same 0.08 divided by 4. Now we get an answer of 158. So now I'm going to divide that, 250,000 divided by answer. And I'm going to get 1581.70. So if t equals 18, then d equals 1581. That's a much smaller number, which equals $525 a month. So here's the thing. By starting 5 years earlier, we now have to put almost half as much in. So 575, that's like 40% less. That's huge difference. An absolutely huge difference. Yeah, we're putting in less money, but for longer, but that money's going to gain more interest. And it ends up being a pretty significant difference in terms of how much of your own money that you're putting in. And if you were to go ahead and calculate the interest on the actual amount of interest in this, you're getting a lot more interest by putting it in for the 18 years because you're putting in much less of your own money. So food for thought when creating an account. The earlier you can start making an account like this, always the better off that you are. Okay, we're almost done here. We have one more kind of problem that we can do. The good news is, if for a problem like this, you'll always be solving mostly for D or for R, but in rare cases, you'll have to solve for T. So let's do a problem where you have to solve for T. Okay, because this will be a logarithm problem. You are able to put $150 per month in a savings account that gains 2.7% interest. How long will it be until you can purchase a $10,000 lake boat? Okay, let's set up the problem. We're trying to get $10,000 for a lake boat. We are able to put $150 per month into a savings account, 2.7% interest, so 0.027. Monthly compounding because it's 150 per month, and T equals, we don't know. Okay, so let's put this in. This one's going to take more work to solve. Okay, so let's write it out. 1 plus 0.027 over 12 to the 12t power minus 1 over 0.027 over 12. Okay. So with this problem here, unfortunately with this one, we're going to have to actually do some bigger solving steps. That's okay though, we can do it, right? So to handle this, we're just going to apply the same kind of problems we did earlier on in the course. So let us start by solving, right? So what's the first thing I have to do to solve for T? I have to divide by 150, right? Let's get rid of this. So we're going to divide by 150. So 10,000 divided by 150 equals 66.6 repeated. Equals parentheses 1 plus 0.027 over 12 to the 12t power minus 1 over 0.027 over 12. Okay. All right, now what's next? Let's get rid of this denominator. So again, we have to, if we need to solve for t, this exponential piece here is the part we're going to have to isolate. So multiply by the denominator. So we are going to multiply by 0.027 over 12. So times 0.027 over 12. And that gets me 0.15 exactly. Perfect. Okay, now that's all on one line. And then all I have to do now, I can add 1 to both sides. And I get 1.15 equals 1 plus 0.027 over 12 to the 12t power. Okay. So at this point, now we should figure out what this number actually is. So let's go here and let's do 0.027 over 12. And that is 0.00225. So now this equation becomes 1.15 equals 1.00225 to the 12t power. Okay, yep, perfect. Okay, now again, if you don't get a nice even number here, just go ahead and round it to as many decimal places as you can. Carry as much as you can. Remember, I usually use 8 decimal places here. Okay, at this point, remember that this is the part where I have to use a logarithm for, okay? So I have to do a logarithm to get rid of this so I can apply t. I need to get rid of this 1.00225. So to do that, I do log 1.15 over log 1.00225. So let's do that. Let's get an answer. So log 1.15 close parentheses divided by log 1.00225. Remember, always close your parentheses with logarithms. Always do it. 62.18. 627363. Perfect. Okay, now this is equal to 12t. This number represents the number of periods needed to actually get the correct amount, which is 10,000. So if it's 62.18 periods, but we know that there's 12 periods in a year, all we do is we just divide by 12. And we get value, just simply divide by 12. 5.18 years. We can round this to 2 decimal places. 5.18 years. Okay, so if you're wondering if there's a general process to solving here, some of you might like just like a list of all the steps that you should always do. Okay, so again, here's kind of the way that you want to do it. All right, so every time you have a problem where you're solving for the log, okay, so maybe I'll just go ahead and type this. Okay, so the very first thing that you want to do is divide both sides by d, by that deposit. Okay, multiply by that denominator, which is r over n. So that's always the second step that you do. Okay. All right, now let's look at the next thing that we did. Okay, once we multiplied by this, the next thing we did is we added the 1 to both sides. Okay. And then after that, that isolates the exponential term. Find log of constant term divided by log of base, that change of base formula. So that log of the exponential base. Okay, and then finally, after that, divide by n, which is that, in this case, that 12. So you're always going to really do the steps in that same order. So when you need to solve for the time, so rather than, I shouldn't say solve for log here, I should say this is when you need to solve for time. Okay, so you'll be doing those steps really in the same order. Okay, and that should never change. Just the numbers change, but the process never does. Okay, so remember, these problems are the same as always, just a new formula, but then you plug all the numbers in, you get a variable, you solve for the variable. The answer, if it's t, will always be years. Okay, this always works. Okay, you'll only ever solve for t or f or d with these problems, never r, because you can't solve for r with it being both in the numerator and the denominator here. Okay, folks, I hope you enjoyed this problem, and hope that it helps you a little bit. And here's one more time the final process for doing this. Um, so actually, it turns out you can actually write this as a formula. For those of you that like to write formulas, um, you could technically do this, and you could write this by saying that t, oh my goodness, hold on. Um, I'm having some issues here. Okay, I'm having just a little bit of issues here. So let's go back. You can actually write this as an expression for t, um, because then it turns out what's going on? What is happening? Okay, all right. So my pen is acting a little strange. Log of the base, but how did we figure that out? It ended up being f over p, um, but then we added the 1, right? So it ended up being, there is kind of a way that you can write this by actually solving for time here. So it becomes f divided by p, or sorry, f divided by d, but then you multiplied by r over n. So it becomes something that looks like this. Um, f, f times r divided by n times d, over log of 1 plus r over n, um, times n itself. So it ends up being a little bit something like this. Yeah, it's a bit crazy. Maybe this is a bit overkill, um, but that technically works. Hey, you never know. Some of you might like that, others might not. But regardless, you can always follow these steps to solve for t. Okay? All right, that's the last thing I'll say here, and I hope that this helps. And go for it. Have fun. Have a good night.